Greetings. In our previous video, we managed to find this equation for the mass conservation law and also this equation for the first law of thermodynamics, and we came to the point to calculate work. Of course, this is a constant pressure work, it's a moving boundary work, so we could calculate work from work equals integral P dV, and that would equal P times V2 minus V1. Of course, please note that in this case, we just are selecting dV since the area is constant and the movement of the piston just is multiplied by force F dx, and that gives us work. As we use dV, it is the change of volume inside this control volume, and what we use does in no way imply that the mass inside this control volume is constant. It is just we are multiplying piston movement by area, and that means the volume underneath this piston without meaning that it is a constant mass. So this is a very simple calculation, and this equals 282.8 times 0.6 minus 0.4, and that is 56.56 kilojoules. That is the work done by the piston, and this work is positive since it's done on the surroundings. Now let's put values into this equation, and a very simple point is that this T2 and this T2 cancels. We come to 591.22 times CV0, which is 0.7184 for air. Of course, we are using air at normal conditions. It would be a very good approximation for CV0 and CP0, minus 1.3 kilograms times CV0, which is 0.718 times T1, which is 303.15, and that equals 591.22 divided by T2 minus 1.3 and times CP0, which is 1.005 times TI, which is 70 degrees centigrade, and that is 343.15, and finally work, which is 56.56. And the only unknown in this equation is T2. Everything else we know. So it is just a matter of calculating T2 from this equation, and I calculated it to be 315.5 kelvins. That's a good point, because once we know T2, then we could calculate other properties at 2. This means that P2 V2 equals M2 R T2. Previously, we didn't know M2 and T2, so we were unable to calculate either of these two. Now that we know T2, we can know also the mass inside the cylinder at this final condition. So it is the pressure remains constant to 82.8 times 0.6, and that equals M2 times 0.287 and times 315.5, which is the temperature we have just calculated for the final condition. And this gives us M2 equal 1.874 kilograms. Since this is the final mass, the mass conservation equation, we know M2, we know M1, so Mi is M2 minus M1, and that equals 1.874 minus 1.3, which equals 0.574 kilograms. And that's uh, our mass that has entered this control volume, and that uh, it concludes whatever we could gain from the first law and the mass conservation law. Our next step should be to go to the second law, this equation, and see what we can gain from that. This is very interesting, and we shall see that shortly. The second law of thermodynamics tells us that we have three terms for entropy, and the equation we had to calculate the change of entropy was S2 minus S1 between any 2 points, 2 and 1, was Cp0 ln T2 over T1 minus R ln P2 over P1. So we have here, you can calculate the difference between two entropy terms. What happens here that we have three entropy terms? And the mass conservation law usually comes to our help in such situations. A similar case happens in heat exchangers when two masses enter and only one mass exits, and you have three entropy terms inside that heat exchanger, and this method will also be helpful in that case. So how do we write it? We write this equation as M2 S2 minus M1 S1, and that equals, replace Mi with M2 minus M1, M2 minus M1 times Si and plus Sgen. So this is a very good form for this equation, since we have four entropy terms, and therefore we could simplify it in this way. This would be M2 times S2 minus Si, S2 minus Si, minus M1 times S1 minus Sy, and that equals Sgen. And now we can apply this equation very easily. It would be M2 times Cp0 ln T2 over Ti minus R ln P2 over Pi, which is in fact this equation written between S2 and Si, minus M1 times Cp0 ln T1 over Ti minus R ln P1 over Pi, which is S1 minus Si, and that equals Sgen. So we could just put numbers into it, and that would be 1.874. This is M2 times 1.005 ln T2, which is 315.5 divided by 343.15 minus R 0.287 ln P2 over Pi, which is 282.8 divided by 500. You see, this term is the contribution of the energy difference, a temperature difference between the entering mass and the mass that is inside. This time is a contribution of the pressure difference, and each of them contributes to the irreversibility and entropy generation, minus N1, which was 1.3 times 1.005 ln T1 303.15 divided by Ti, which is 343.15 minus 0.287 ln 282.8 divided by 500. The pressure difference doesn't change since there is no change in the pressure of the incoming air, and there is no change in the pressure inside the cylinder. So the pressure difference remains the same and has the same contribution. I would calculate these terms independently, and there's a point to it. The equation would be 1.874 times 0.0791. This means that the entropy for 2 is larger than entropy for I, minus 1.3 times 0.039, which means that entropy for 1 is also larger than entropy for I. Okay, and that equals Sgen. And the outcome is that Sgen equals 0.0975 kilojoules per Kelvin, which is the total generated entropy through all this process. The final step that we should take and we always do is to draw the TS diagram. That has a lot to teach us. I draw the TS diagram here. This is our TS diagram, and there are two constant pressure lines of interest to us. One is the line for the pressure P equals 282 points. The line for the pressure 282.8 kilopascals, and another line is for pressure P equals 500 kilopascals. These are the two constant pressure lines. Point 1 is here, perhaps. This is point 1, where temperature is 303.15, and I put a Kelvin here so that all temperature values that I point are in Kelvins. Now, to put point I on this diagram, we have to know whether I has entropy less than 1 or more than 1. And that's why I calculated this term individually. I calculated this term individually and put the value for it. And as it is positive, we know that 1 has larger entropy than I. So if this is 1 and has larger entropy than 1, then this would be I with smaller entropy. The temperature for I is 343.15, and we know the temperature for 2. The temperature for 2 is somewhere in between. It is 315.5 kelvins, and so this is point 2. The mass inside this cylinder, the mass that initially was inside the cylinder, goes through a process like this. It has constant pressure, its pressure remains constant, and therefore the process goes from 1 to 2. But what's the process that happens to the mass that enters this control volume? Initially, it is point I to 1. This is the initial process, but gradually, as the mass inside this control volume changed from 1 to 2, then the process also changes from 1 to 2. So this is the initial process, and this is the final process. How do we denote these two processes? Very, very simple. For any process, these are polytropic processes. You see, this is the isentropic process. This process is isentropic process. And these two processes are polytropic processes. For a polytropic process, we could write Pi over P1, say for the initial polytropic process from I to 1, we could write Pi over P1 is Ti over T1 to the power n over n minus 1. So these two red processes I would denote again here as polytropic process. These two are two polytropic processes with different values for n, and we could easily calculate these values simply by writing that ln, we take logarithms from natural logarithms from both sides, and that is ln of pi, which is 500, divided by p1, which is 282.8, and that equals n over n minus 1, ln ti over t1, which is 343.15 divided by 303.15. And the outcome of this equation is n equals 1.278. That is for process I21, which is this one, which is this process. And if it was this process, you see, for this process, n equals gamma equals 1.4, which is a property of air. For this process, we have just calculated that n equals 1.278. What happens for this process? I would just write it here for the final product, and gradually, as the air enters the cylinder, our process moves from this one to this one. So we have processes all through these area. Okay, this is the middle process, and this is the final process. So for the final process, which is I2, we write ln pi over p2 equals n over n minus 1 ln ti over t2. Putting numbers to it, ln 500 divided by 282.8 equals n over n minus 1 ln ti, which is 343.15 divided by 315.1, which is t2, and that gives us n equals 1.173. You see, this process had n equals 1.278, and this process, which is another polytropic process, has n equals 1.173, which is even farther away from an isentropic process. So we managed to do all the steps that we had to take for solving the problem. We decided on the control volume, we calculated properties, then we simplified our equations, the mass conservation law, first law of thermodynamics, and the second law of thermodynamics. We used these equations to calculate final temperature and also final pressure, and then we use the second law of thermodynamics to calculate the entropy generation. It is different initially and finally, and we now know what the entropy generation initially was. This was the initial entropy generation, and this is final entropy generation per unit mass. And you see, it's interesting that the initial entropy generation per unit mass is smaller, 0.039, and the final entropy generation per unit mass is larger, 0.0791. So, in fact, as the problem proceeds, we have larger entropy generation per unit mass. Well, thank you very much for watching, and cheers.